The 1925 paper by Werner Heisenberg, titled Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations, represents a conceptual pivot of immense consequence in the history of science. It functions less as a complete theory and more as a foundational manifesto, a daring and abstract program for constructing a new physics. This essay will undertake a profound evaluation of the internal claims, arguments, and specific logical maneuvers presented within that seminal work. The analysis will proceed sequentially through the paper's core sections, critically examining the architecture of Heisenberg's reasoning and the intellectual courage embedded in his proposed calculus. The objective is to illuminate the paper's persuasive power by dissecting the precise steps through which it sought to establish a coherent quantum mechanics built upon the austere principle of relating only observable quantities. We will explore the framework as Heisenberg himself laid it out, assessing the validity and ingenuity of each proposition in its immediate context, thereby appreciating the work's self-contained, revolutionary logic as a monument of theoretical physics. Section 1. The foundational commitment to observable quantities. Heisenberg initiates his argument with a statement of profound epistemological commitment, a principle that governs every subsequent step of his analysis. He proposes that rational quantum mechanics must be constructed exclusively from quantities that are, in principle, observable. This opening claim is the philosophical bedrock of the entire paper. He identifies the frequencies and amplitudes of light emitted and absorbed by atoms as prime examples of such observables. Concurrently, he identifies concepts like the precise position and period of an electron in its orbital path as theoretical constructs lacking any direct empirical correlate. His evaluation is that the persistent paradoxes of the existing quantum theory, a hybrid of classical mechanics and ad hoc quantum rules, stem directly from the retention of these unobservable kinematic descriptions. The central argument of this introductory section is that a consistent theory emerges from the formal translation of the relationships between classical quantities into relationships between their quantum mechanical, observable analogues. This is a claim of methodological power. The very structure of the new mechanics can be discovered by insisting on this translation. He implicitly critiques the pictorial appeal of the Bohr model, suggesting its intuitive nature is a liability that perpetuates a reliance on a defunct mechanics. His evidence for this claim is the success of recent work on dispersion, particularly the formalism developed with Kramers. The Kramers, Heisenberg, dispersion formula relates an incoming photon scattering behavior to a collection of virtual oscillators corresponding to all possible quantum jumps an atom could make. The formula itself is a catalogue of observable transition amplitudes and frequencies, and its empirical success provides Heisenberg with a concrete example of a physical law expressed, without reference, to electron orbits. He leverages this as proof of concept, arguing that the same foundational thinking should be applied to fundamental mechanics itself. The power of this section's claim lies in its clarity and audacity. It redefines the goal of physical theory from representing a hidden reality to formulating a consistent calculus for predicting experimental outcomes. Section 2. The reinterpretation of kinematic variables and the new multiplication rule. This section contains the paper's most radical and creative intellectual leap, the translation of classical kinematics into a new symbolic language. Heisenberg considers a classical quantity, such as the position of an electron, which would classically be represented as a function of time. Through Fourier analysis, this position function can be expressed as the sum of oscillating components, each with a specific frequency and amplitude. He begins his reinterpretation here. In the quantum case, he argues, the observed frequencies do not correspond to the harmonics of a single fundamental orbital frequency, but to the transitions between two distinct stationary states, say from a state n to a state m. Therefore, he proposes that the quantum theoretical counterpart to the classical position variable should be represented as a collection of quantities indexed by two states. He envisions a two-dimensional array, or table, where each element, which we might write as x with subscripts n and m, represents the amplitude associated with the transition from state n to state m, oscillating with the frequency omega sub nm. This is a monumental conceptual move. A single, time-dependent variable is replaced by an infinite, static array of transition components. The claim is that this array constitutes the complete quantum definition of the physical quantity. Having redefined kinematic variables, Heisenberg confronts the immediate problem of how to manipulate them. Specifically, how does one calculate a quantity like position squared, or the product of position and momentum? In classical physics, this is trivial multiplication of functions. In his new scheme, it requires a rule for multiplying these arrays. He posits a multiplication, law derived from physical intuition. If one considers the array representing the square of the position, x squared, its component for a transition from state n to state m should be constructed by considering all possible intermediate states. An electron could transition from state n to some intermediate state k, and then from that state k to the final state m. He proposes that the overall amplitude for the n to n transition is the sum, over all possible intermediate states k, of the products of the individual transition amplitudes. In symbolic language, the component x squared sub nm is the summation over k of the product of x sub mk and x sub km. This is the paper's central technical innovation. Without recognizing it as such, Heisenberg has independently invented the rule for matrix multiplication. The profound implication, which he immediately grasps, is that multiplication in this new mechanics is non-commutative. The product of array x and array y is different from the product of array y and array x. This is a direct consequence of his multiplication rule. The claim here is twofold. First, that this array representation is the correct quantum analogue of a classical variable, and second, that his physically motivated summation rule is the correct law for their combination. The evidence he provides is internal coherence and the expectation that this new calculus will resolve existing problems, a promise the subsequent sections aim to fulfill. The quiet drama of this section resides in the discovery of non-commutativity, a feature with low analogue in the classical world, emerging organically from a strict adherence to observable transition quantities. Section 3. The quantum condition and the derivation of a sum rule. In this section, Heisenberg seeks to connect his new, abstract formalism to the established principles of the old quantum theory, thereby demonstrating its legitimacy. He addresses the Bohr-Sommerfeld quantization condition, which in its classical form involves integrating momentum over a closed path. This formulation is untenable in his new system, as the concept of a path or trajectory has been deliberately excised. He must find a quantum mechanical analogue of this condition, expressed entirely within his new language of arrays and transition amplitudes. His approach is ingenious. He examines a classical expression and differentiates it with respect to a classical action variable. Then, he translates this differentiated expression into his quantum language. Through a clever series of manipulations involving his new calculus, he arrives at a remarkable result. He derives a sum rule involving the squares of the absolute values of the transition amplitudes, weighted by their corresponding frequencies. Specifically, he shows that for a given state n, the sum over all possible final states k of the difference between the square of the amplitude for the transition from n to k and the square of the amplitude for the transition from k to n is equal to a constant, Planck's constant divided by 2 pi. This equation is a pivotal achievement of the paper. Max Born and Pascual Jordan would later recognize it as the diagonal elements of the infamous canonical commutation relation. The commutator of the position operator q and the momentum operator p equals I times h bar. Heisenberg, working alone, derived this foundational pillar of quantum mechanics without the formal language of operators or commutators. His claim in this section is that his new mechanics internally generates the essential quantization constraint that was previously imposed upon classical mechanics from the outside. He provides a direct link between the old and new theories, showing that his system reproduces a known quantum result, albeit in a novel and more fundamental form. The persuasive power of this section is immense. It demonstrates that the abstract rules proposed in the previous section are not arbitrary mathematical games. They possess the precise structure needed to encapsulate the core quantum phenomena embodied in the Bohr-Sommerfeld conditions. Furthermore, he makes a critical connection to the Thomas Kuhn sum rule, an established result from dispersion theory. He shows that his derived quantum condition is essentially a more general form of this sum rule, lending his result further credibility by grounding it in a known, successful physical relation. The evaluation of this section's argument is that it provides the crucial bridge, validating the new kinematics by showing it could reproduce, and even deepen the understanding of, the quantum constraints that defined the previous era of physics. Section 4. The application to the anharmonic oscillator and energy conservation. Having established the foundational principles and the core quantization rule, Heisenberg devotes the final substantive section to a practical demonstration of his method's power. He applies his new calculus to a concrete physical problem, the anharmonic oscillator. This choice is strategic. The simple harmonic oscillator, while solvable, has special properties that could be misleading. The anharmonic oscillator, which includes a term proportional to the cube of the position in its potential energy, a more realistic and challenging test. It was a problem that had posed considerable difficulties for the old quantum theory. The primary claim of this section is that his formalism provides a systematic, if laborious, method for calculating the stationary energy states and the transition amplitudes for such a system. He begins by asserting that in his mechanics, the principle of energy conservation holds for isolated systems. This means the array representing the total energy, or Hamiltonian, must be diagonal. All its off-diagonal elements, which correspond to transitions, must be zero, as energy cannot change in a stationary. Heisenberg then lays out a procedure. He writes down the Hamiltonian for the anharmonic oscillator, translating the classical position and momentum into his new array language. The equation of motion, he argues, is the quantum analogue of Hamilton's equations. He then solves these equations using a method of successive approximations. He starts with the known solution for the simple harmonic oscillator and treats the anharmonic term as a small perturbation. His new multiplication rule is put to the work of calculating the corrections to the energy levels and the transition amplitudes. The calculation is intricate, a cascade of summations and algebraic manipulations of the array components. Ultimately, he finds that the energy of the nth state contains a term proportional to Planck's constant squared times the quantity n plus 1/2 squared. This result for the energy levels was significant success. It demonstrated that the formalism could yield discrete, quantized energy states directly from the mechanics, without any ad hoc assumptions beyond the initial setup. He also correctly deduces selection rules, showing that certain transitions have zero amplitude and are therefore forbidden, a key feature of atomic spectra. The internal claim is validated by the result the abstract symbolic machinery, when applied to a specific physical system, produces physically meaningful and quantitatively plausible results. The evaluation of this section's argument highlights its crucial role as a proof of concept. While the calculation was arduous, success served as powerful evidence that Heisenberg had discovered a genuinely new and workable system of mechanics. It transformed his work from a set of abstract philosophical and mathematical proposals into a tool with demonstrable predictive power, paving the way for its immediate and explosive development. By conclusion, Werner Heisenberg's 1925 paper on the reinterpretation of kinematics stands as a work of profound intellectual construction. Its claims are presented with a relentless, self-contained logic that systematically dismantles the conceptual apparatus of classical pictures and erects in its place an abstract and powerful symbolic framework. The initial commitment to observable quantities is not merely a philosophical preference, it functions as a generative principle, forcing the creation of a new mathematical language. The evaluation of the paper's core claims reveals a chain of reasoning of remarkable integrity, the redefinition of physical variables as arrays of transition components, a deeply non-intuitive step, leads directly to the discovery of a non-commutative multiplication rule. This new calculus, in turn, is shown to contain within its structure the very quantization condition that had been an external postulate in the old quantum theory. Finally, the application of this entire machinery to the challenging problem of the anharmonic oscillator demonstrates its practical viability, yielding discrete energy levels and selection rules from first principles. The paper's lasting significance derives from the success of this internal program. Heisenberg presented a scheme that was mathematically incomplete and computationally demanding, yet philosophically coherent and predictively potent. He did more than solve a problem. He redefined the very nature of a physical theory, shifting its focus from pictorial representation to the formal relationships between observable phenomena. The work's genius lies in its procedural audacity, providing a complete, if embryonic, blueprint for the new quantum mechanics, a calculus whose profound implications would reshape the 20th century's understanding of reality.